Workshop. Hi, I'm David. Engine management systems have come a long way in a relatively short time. Manufacturers have been driven by the goals of lower emissions and better fuel economy to develop the systems we have today. In this module, I'll be concentrating on the system sensors. The heart of the engine management system is the Engine Control Module, or ECM. The ECM receives signals about the engine parameters from the sensors and sends out controls to activate various components. In the modern engine management system, the sensors can include a mass airflow sensor, intake air temperature, engine coolant temperature sensor, manifold absolute pressure sensor, accelerator pedal position sensor, throttle position sensor, camshaft position sensor, crankshaft position sensor, oxygen sensor, NOx sensor, low pressure fuel sensor, and fuel rail pressure sensor. In this module, the schematics and sample waveforms are typical of most vehicles. Always remember to check the correct information for your particular vehicle. The mass airflow, or MAF sensor, directly measures the engine's air intake. This signal is used to calculate the required amount of fuel and to monitor the exhaust gas recirculation if fitted. In the future, even more rigid emission legislation and the demand for lower fuel consumption will require further increased signal precision and diagnostic capabilities. There have been several different types of sensors. Earlier designs, like the Vane and Kármán Vortex, only measured the flow of air, not the mass of air. A hot wire sensor determines the mass of air flowing into the engine's air intake system. This is achieved by heating a wire suspended in the intake airstream, with either a constant voltage over the wire or a constant current through the wire. The wire's resistance increases as the temperature increases. When air flows past the wire cools, decreasing its resistance, which in turn allows more current to flow through the circuit or causes a smaller voltage drop over the wire. The sensor converts the measurement into a signal that is sent to the ECM. A hot film type MAF sensor measures the air mass going into the engine. Only a part of the air is measured. The air to be measured enters a curved tube. This prevents return pulses being measured. This type of sensor uses a hot film that is cooled by air flowing past the sensing element as it enters the engine. There is a centrally heated film or metallic grid type element. On either side of the element are temperature-sensitive resistors. The resistor on the air filter side will be cooled by the incoming air, and the one on the engine side will be heated by the air passing over the element. The difference between the two is measured and relayed as a square wave digital frequency signal to the ECM. A sample waveform can be seen here. The latest MAF sensors incorporate barometric and humidity sensors and are often referred to as mini weather stations. These sensors send temperature and humidity data along one signal wire. The humidity is sent as a changing duty cycle and the temperature as a changing frequency. Here is a typical circuit of a MAF sensor that incorporates the intake air temperature, or IAT sensor. The IAT is a negative temperature coefficient, or NTC thermistor. As the temperature goes up, the resistance of the sensor goes down. The IAT sensor has a signal circuit and a low reference circuit. It measures the temperature of the air entering the engine. The ECM uses this signal to make minor corrections to the operating parameters. Some turbocharged engines use a second IAT sensor after the turbocharger. This allows for the comparison of the intake air to the boosted air temperature. The engine coolant temperature, or ECT sensor, like the IAT sensor, is an NTC thermistor. The ECM supplies 5 volts to the ECT sensor signal circuit and supplies a ground for the low reference circuit. The ECT sensor signal will allow the ECM to monitor engine temperature and adjust control parameters during open loop operation. The manifold absolute pressure, or MAP sensor, is a 3-wire sensor. This sensor detects and relays the manifold pressure of the engine to the ECM. During key on, when the engine is not running, the manifold is under atmospheric pressure, and the MAP sensor can use this as a barometric pressure reference. Some vehicles will have a separate barometric or baro sensor. The output of a MAP sensor can be either a variable voltage or a changing frequency. The ECM uses the MAP signal for fuel delivery, canister purge, spark timing, and barometric pressure readings. The accelerator pedal assembly contains 2 accelerator pedal position, or APP sensors. Each APP sensor has a 5-volt reference, a low reference, and a signal circuit. The APP sensors provide a signal voltage that changes relative to pedal position. The 2 signal voltages may go in the same direction with the same readings, the same direction with different readings, or opposite directions. The throttle body assembly contains 2 throttle position sensors. These provide signal voltages that change relative to throttle blade angle. The ECM supplies the throttle position sensors with a common 5-volt reference, a common low reference, and 2 independent signal circuits. The throttle position sensors will usually have opposite functionality. The ECM uses these signals to confirm that the throttle butterfly has been moved to the correct position. Later type throttle body assemblies contain a non-contact throttle position sensing element that is managed by an integrated circuit. The throttle position sensor provides a voltage signal that changes relative to throttle blade angle. The integrated circuit translates the voltage into serial data using the single edge nibble transmission, or SENT protocol. The ECM decodes the serial data signal into separate voltages. The crankshaft position, or CKP sensor, can be an inductive sensor producing an AC waveform of different amplitude and frequency, or a Hall effect sensor creating a digital on-off signal of varying frequency. There is usually a reluctor wheel reference gap to identify top dead centre, or TDC. The ECM uses each crankshaft position signal pulse to determine crankshaft speed and position. This information is then used to determine the optimum ignition and injection points for the engine. The ECM also uses the crankshaft position sensor to detect cylinder misfires. The camshaft position, or CMP sensor, produces a digital on-off signal of varying frequency. The frequency will depend on engine speed. Combined with the CKP sensor, the exact position and stroke of the crankshaft can be determined. On vehicles with variable valve timing, the ECM can confirm the relationship between the crankshaft and camshaft. The heated oxygen sensors enable the ECM to measure oxygen content in the exhaust stream. The ECM uses this information to accurately control the air-fuel ratio. The signal from an upstream sensor, fitted before the catalytic converter, is used to make fuel mixture adjustments. A downstream O2 sensor, or one that's fitted after the catalytic converter, is used to determine catalytic efficiency. The O2 sensor heater circuit is controlled by a pulse width modulated signal from the ECM. The NOx sensor enables the ECM to control the ignition timing for the best possible performance while protecting the engine from potentially damaging detonation. The sensor uses a piezoelectric crystal that produces an AC voltage signal. The amplitude and frequency of the signal will depend upon the level of knock that is detected. If a knock is detected, then the ECM will retard the ignition timing by a programmed amount. Once the knock is no longer detected, the timing will be returned to normal in small increments at programmed intervals. The fuel rail pressure, or FRP sensor, detects the fuel pressure within the fuel rail. There is a 5-volt reference, a ground or low reference, and a signal circuit. The varying signal is sent to the ECM. Fuel pressure will be adjusted in response to this signal. Not all vehicles will have an FRP sensor. These sensors are commonly used on direct petrol-injected engines. Some vehicles use a low-pressure fuel sensor. This sensor is a 3-wire piezoresistive unit with a 5-volt supply, low reference, and signal circuit. On direct injected engines, it's located in the fuel line between the low pressure and the high pressure pump. On vehicles that use variable injection duration and variable fuel pressure, the sensor will be located between the fuel pump and the fuel rail, or in the fuel rail itself. Other sensors that may be used are engine oil level, engine oil pressure, and engine oil temperature. And there you have an overview of the sensors associated with petrol engine management. In another module, we'll be looking at the fuel delivery system of the modern petrol engine. Knowing how these sensors and systems work will help you when it comes to their repair. And remember, training is the key to your success. Bye for now.